Hello and welcome everyone. In this session I will talk about coaxial controls, but before that let us see how to define datums on coaxial features. So suppose we have a shaft here. So what does this shaft do is, it rotates about these two shafts here. So it will rest on these two shafts here and then it will rotate. So how do we define datums on such kinds of features? So in this case what I have done is I have defined both of these shafts as my datum. So I have said that the diameter of these shafts is 10 plus minus 0.1 mm, and then I define the position tolerance of 0.05 at maximum material condition, and both of these are my datum A. So it's just like what we did in our holes. So we define both of these holes as datum A. So what we will do is we will level up this shaft to the best alignment, and then the axes of these two shafts shall lie within 0.05 mm tolerance range. So let us say that this was our part after manufacturing, and as you can see that these axes are tilted a little bit. So let us see how we will align this. So first I will level up this part and I will take the smallest cylinder which fits on this shaft. So this will be called as my datum simulator, and I will take another smaller cylinder which will fit into this shaft here. So like that I will have an axis of this. Now I will take the smallest cylinder which can have both of these inclined axes here. So this will be my smallest cylinder and this will be axis for my part, and this tolerance range is 0.05 mm. So you can see that this part will now fit in this. Now I will set this part into this virtual size. So this is my virtual size, and I will put my part into this one. Now you can see that how these axes are inclined. Still we are falling under the virtual size. So what will be the virtual size in this case? 10.1 plus 0.05, that will give us 10.15. So this will be my virtual size, and my part will rest something like this, and this tolerance range will be 0.05 mm, and this will extend up till here, and this tolerance range will cover both of these axes. Now some people define this as my datum A, and then they locate this shaft here and then they name it as datum B. So look what happens when I define this as my datum A. So if I define this as my datum A, see how this shaft goes upwards and everything gets messed up. So whenever you have any shaft which rotates on both ends, in that case define both of those shafts as the same datum, and then take the smallest cylinder which passes through both these axes, and that will be our tolerance range. So instead of defining one as datum A and then locating another shaft and then defining that as datum B, so always define like this, both the shafts should come as datum A. And there is one more method by which you can show this. You can also show it like this. This is your datum A and this will be your datum B, but in the feature control frame you will write as A-B. That means both are aligned to each other. So this or this, both are same. Just remember, you do not define this as datum A and then locate it with respect to datum A. These should be located to each other, that is A-B. And then this axis you can call it as axis for A-B. So that's how you define datums in coaxial shafts. And in the next session we will see the difference between position, runout, total runout, concentricity, and profile. So we'll see the difference between all of these, and we will study more about coaxial shafts. So that's it in this session. If you have any doubts, let me know, and see you in the next session.